So I think we're moving on to the next, to our keynote speaker. Is that correct, James?
Yes, go ahead. The recording is going.
All right. And I'm checking to see if our keynote speaker is here.
Yes,
That's
Lauren
me.
Laufman. She's here. She's
Yeah,
waiting.
there you are. Okay. All right. So Lauren is our keynote speaker. Lauren is a graduate student here at the University of Minnesota Twin Cities. And the talk is actually, I've seen a version of it before, and it's actually a really, really interesting and very topical talk. It's about the large number of small spacecraft that are being put into low Earth orbit and what their impact is going to be, or are they going to have an impact on astronomy in the future? So I'm not going to steal any more of your thunder. So it's all yours, Lauren.
Thank you. Let me share my screen with the Chrome window. Share, and then click present. Can y'all see the title slide?
Yes,
cool.
Go ahead.
Thanks. All right, so my talk is called Starlink, the Loss of Our Stars. And this talk is going to cover first, what is Starlink? Then I will go into depth about a case study with the Lsst telescope. And then finally, I'll go into the costs and benefits of having satellites like this in low Earth orbit. So first off, what is Starlink? In case you haven't already heard, Starlink is a constellation of satellites created by Elon Musk and launched by SpaceX into low Earth orbit. The goal of Starlink is to provide global internet access to everyone. Their orbital altitude is approximately 550 kilometers. The plan is to have, several thousand, like 40,000 of these, which is why it's called a satellite constellation. But the main problem with Starlink is that they are extremely reflective and visible in telescope images. So here we have a diagram showing how the sunlight comes in and bounces off the satellites, but I'm going to break it down for you just a bit more to make it more intuitive. So you've got Earth, you've got some atmosphere, and the sun over here is shining on the day side of Earth, and then you've got night side on the right. Now you stick your telescope down and you're trying to look at the sky, you're trying to see some cool galaxies and stuff, but there's a Starlink satellite. So the sunlight will come in and it bounces right off of the Starlink satellite and down into your telescope. This is a problem because while the satellite is on the night side of Earth, it has not yet entered Earth's shadow. So it's very clearly reflecting the sunlight. So in this region, kind of where I put the red box, and likewise on the other side, satellites like Starlink, which are ultra reflective, will ruin telescope images. So I'm going to show you part of a quick video showing the Starlink satellite train, one that was freshly launched, in the sky. You can see all these other stars in the background, but the long vertical line of dots are the Starlink satellites as they are ascending to their full orbital altitude. They are extremely bright, around like third magnitude, or sometimes even second actually. But yeah, I will not subject you to the whole video because it's just watching dots march across the sky, but it is quite dramatic to actually go out and see for yourself. Now, from the point of view, that was from you looking at the sky, but here is what it's like if you are a telescope trying to take a long exposure image of the sky, and you get an entire train of those going across the field of view. This image specifically is from the detector on the dark energy camera on the Blanco telescope down in Chile. So let's move into the next part of the talk, which is the original format I gave this talk in earlier, and it is called Lsst, a case study. It particularly delves into a paper by Tyson et al. That examine what effect will Starlink have on Lsst, better known as Vera Rubin Observatory, or the Large Synoptic Survey Telescope, which is currently under construction in Chile, and the primary mirror is 8.4 meters in diameter. This telescope is huge. Like, I don't know if you've seen telescopes in person, but this is really big. Anyways, it has a 3.2 gigapixel CCD imaging camera, which for comparison, your phone maybe has 50 megapixels at best. Its goal is to photograph the entire available sky every few nights. And to do this, the survey will take 15-second exposures every 20 seconds. Now, what's important to keep in mind is how does this do this? Because this telescope, the goal is to be entirely automated. So it will be scheduling observations in near real time using a Markov decision process. There's a simulation that takes into account the mechanical model of the telescope, the weather, the downtime, but it has to balance a number of factors. For one, it needs a uniform survey footprint. So it would be kind of bad if it took photographs of this one area of the sky a lot of times, but this other area of the sky like no times. That would not be good. We also want to minimize the slewing time. Slewing is the time it takes to move the telescope from one area to the next, also referred to as overhead time. We also want to observe lower air mass regions. So if your telescope is pointed directly up, there's a lot less atmosphere between it and space than if you're looking at something on the horizon. And the more atmosphere there is between you and your target, the worse your image. And last of all, we want to minimize the number of filter changes because LSST has filters. Imagine like a big piece of glass in different colors and you stick it over the camera. That's important to astronomy, but I won't get into why. However, satellites throw a bit of a wrench into this plan. So one group did a simulation of 12,000 and 48,000 Starlink satellites at an orbital altitude of 550 kilometers to see how that would affect the LSST telescope. Right here, with the maximum planned 48,000 satellites at 550 kilometers, about 30% of all LSST images will have at least one satellite trail. That's really bad. And then typically, a satellite trail traverses 13 to 16 of the camera's 189 CCDs. CCDs are the cameras right here in my fancy little slide thing right on the left. Each of these little rectangles is a CCD for context. So there's 189 of those for LSST, and a single satellite trail could ruin 13 to 16 of those. You would have to be masking nearly 1% of pixels in an entire image. This figure here on the right is a more easy to demonstrate, to understand image. So the y-axis is the fraction of exposures that have a satellite present, and the x-axis is just days of the year. So right here is January 1st in the middle of winter. And in this case, at midnight, no matter what, you will have satellite images. Just also, sorry, winter for the Southern Hemisphere. I forgot to mention that. So winter in the Southern Hemisphere is the nights will be the shortest. And so when the nights are short, you're stuck with satellite trails in everything. Like you will have them. Now, say during the summer over here, where the nights are longest, in the middle of the night, you won't necessarily have satellite trails, but you'll still have them like at twilight. And you might ask, why would astronomers take images at twilight? Trust me, it's an astronomy thing. You need to take them for calibration, as compared to at midnight where you're actually getting your observations. So there's a suggested satellite avoidance strategy. Let's check to see if a satellite is expected to cross during an exposure. If the crossing will occur, pause for 10 seconds to let the satellite pass, and try again. If it keeps happening, give up after 3 attempts and move on to the next target. This is not great because your twilight flats are your twilight images for calibration are pretty much all going to be contaminated regardless. Like you have to avoid so many and you're going to get so many fewer observations. Baseline of no dodging is you'd take 22,000 like photos of the sky. If you're dodging a 12,000 satellite constellation, you're now only getting 18,000 observations, which you're going at 80% efficiency. And now if there is a full 48,000 satellite constellation, you're only getting 6,000 observations. This is a 26% efficiency. This is incredibly frustrating. Another issue with this is that satellite avoidance requires that the satellite operators make location data publicly available, which not all of them are necessarily willing to help and cooperate, and there is nothing forcing them to, as far as I'm aware. In addition, most of the observations need to be taken in 20-minute pairs. This is to help identify moving objects in the solar system, such as asteroids and whatnot. Planning around these satellites would also require even more slewing time, because if you try to avoid it and go to a different spot in the sky, you now have to slew all the way over to there, and the time it takes to slew is time added on. Right here on the left is an image of, it's an all sky projection map showing 10 minutes worth of satellite streaks just after twilight at Rubin Observatory on a randomly chosen date. Gray is below the horizon, but you can see here that this is just 10 minutes and you basically can't get observations here. There's so many satellites. It's very frustrating to me as an astronomer. I'm actually very emotionally invested in this, which is why I may seem to be talking very forcefully, but I really care. So what the Tyson et al. Paper went into was simulating the Lsst camera's response to trails, since technically the telescope is still under construction. So a lot of features of this paper had to be simulated for what the effect will have. And also because not all the satellites have been launched yet, thankfully. So first, we need to know the peak trail brightness in electrons per pixel for low Earth orbit satellites as a function of the satellite's apparent magnitude. Magnitude, in case you're not an astronomer, is just a measure of how bright an object is. And the satellite apparent brightness depends on a lot of factors: the telescope zenith angle, the distance from the telescope to the satellite, the phase angle, the satellite's geometry, what orientation it's facing, and how much it reflects. So right here, we have an equation that they use to calculate this. And, oh, whoops, I did not mean to go ahead. Yeah. And so it takes into account all of these kind of things, and it figures out like the angular, how far it'll be across the sky, and all this information. Now, you may wonder why this simulated trails cross-section over pixels is kind of double peaked. It's because the satellite is technically out of focus. Telescopes, when they're in focus, will be looking at stars, which are or galaxies, but those are very far away. And so when you have something close up or it's out of focus, it kind of just looks like a donut. And that's how you know you've made a mistake, if you're actually observing and everything looks like a donut. So what they simulated for this is by taking a satellite that is approximately 2 meters wide. The altitude is 550 kilometers. It's seen at a 40-degree zenith angle, and we use Lsst's 8.4 meter primary mirror. What we end up getting is that the full width half max of the trail on your image, so basically how wide is each of these little satellite streaks in the column on the left, it's 2.6 arc seconds. Now, a star itself, if you just have a point and it gets spread out a little because of the atmosphere, would only be 0.7 arc seconds. So what this means is that your satellite trail is like 3 times, actually almost 4 times as wide as a single star. So like at that point, you can't really just subtract the trail from a star. You've completely obliterated it. Right here on the right is just showing the same thing, but more clearly, it's just the width of your simulated trail cross section is so much wider than your star's cross section itself. Yeah, so that's frustrating. So next up, these are kind of hard to explain if you don't already know what magnitudes are and how all this works, but I'm going to try and explain it to y'all. So figures 5 and 6 from the Tyson et al. Paper have the peak counts in satellite trail versus apparent AV magnitude in optical bands. What this means is that if your stuff is way too bright, if you're getting 10 to the 5 electrons per pixel, at that point you have saturated the pixel and you are in trouble. So if you look at, for example, we start with satellite apparent magnitude of 3 in the top graph, and you just walk straight upwards. At saturation, so if the satellite's apparent magnitude in the sky is 3, your green, your red, and your I band will all be saturated. However, like the ultraviolet bands will be not quite saturated, but it's still bad. However, it's still bad because it's above that gray box on the bottom, which is ranges of correctable crosstalk, which I'll get to in a second. But it basically means we can't subtract this without artifacts. And above the black dotted line means we can't subtract this at all. It's a disaster. So what you should take away from this plot is that you need your satellites to be at least like dimmer than 7th magnitude, which, yeah, that's quite a goal to achieve. This bottom plot is also for if the satellites were at 1200 kilometer altitude instead of 500, because there were original plans for Starlink to actually be at a higher altitude, and there are still other projects that may launch at that altitude, which you might think, oh, cool, they're further away, so they're not as bright. Unfortunately, well, since they're further away, their apparent velocity across the sky is a bit slower. So they're spending more time in each pixel. So they're actually even brighter, which is even more frustrating. So masking, can we actually do this? If we want to be extra conservative and make sure that we're getting rid of the peak of the trail and kind of out to the sides as well, you want to do this where the streak counts are greater than 1% of the sky's background noise. Goals of having a residual surface brightness systematic error target of 1 single electron per pixel. So right here at this plot on the right, if you take, for example, the satellite apparent magnitude of 7, which is our darkening goal, and you walk it up for the green band, that means your trail width can only be, you'd have to mask out to 30 arc seconds, which is a lot, relatively speaking. So yeah, oh yeah, and this is for the 550 kilometers. If you start at 10th magnitude, yeah, each of these you just have to keep masking out more trail, in other words. So thankfully, SpaceX did actually start to make some efforts of, all right, I suppose we'll darken these satellites. Maybe we'll try. So to be clear, the satellites themselves aren't emitting light. As we established from my really cool graphic on the first slides, the sunlight is reflected off of the satellites. This is the source of the observed signature. There are 2 types of reflected light that we get from the satellite, and those are specular, which is mirror-like, and diffuse, which is spread over a wide solid angle. You might ask, why were they so darn reflective initially? Turns out it's because they were designed to reduce absorptivity in order to maintain a cool temperature, which makes sense. Like when you think about that one weather satellite that broke because the cooling systems didn't work. That's not relevant at all, but it isn't a thing. You don't want your satellites to be too hot. That's not good. So they launched something called Darksat, which was their initial trial of darkening the satellites, also known as Starlink 1130, January 2020. So the parts that they were able to like paint black, so to speak, were the thermal control radiator, the bare metal anodized aluminum surfaces, and the antennas, and I need a drink of water. And there were an additional 18 satellites in that launch group where they darkened some of them, but not all the surfaces. So they were kind of like not quite Darksat, but not quite original. And right here on the right is a figure of the phased arrays that were darkened. Not covered in this paper, but I'll cover in a few slides, is also VisorSat, which was an alternate attempt to darken the stuff. But VisorSat uses an external radio frequency transparent sunshade to block the sunlight from ever reaching the reflective parts. However, studies seem to show that it has an equivalent reflective brightness to Darksat, but I will get to those numbers in a sec. Observations of Darksat versus regular Starlink. So they measured, they used the Blanco 4-meter telescope's dark energy camera, which is, again, the thing that is the left column of my slides because it looks pretty, but they used that camera to get G-band observations of Darksat. They did several then calculations based off of this to extrapolate how bright it would be if it had appeared at zenith because they were viewing it at an angle, blah, blah, blah. They did some more stuff. And the magnitudes that they resulted in was that it was fainter because the regular satellites were around 5 magnitudes, but Darksat was 6. So that's like 1 magnitude fainter, which isn't great, but it's better, but it still doesn't reach our target goal of 7 or 8. Here are specific measurements comparing Darksat to some of its companions, demonstrating a 1.1 magnitude reduction of brightness. So stationary mag just refers to the magnitude if the satellite were not moving. And so they just kind of extrapolated some stuff and did calculations. Zenith magnitude is what the stationary magnitude would be if the satellite were at zenith, which means directly above you in the sky. And yes, it is 1.1 magnitudes dimmer than the companions, which are the semi-darkened versions, which are 0.5 magnitudes dimmer than the original Starlink satellites. But I would just like to reiterate 10 more times that the darkening goals from that earlier plot were 7th magnitude. This is at best 6.2. Here are some further measurements that a different group did of simulations in actual flux units. So in case any of you prefer actual flux to magnitudes, because I'm an astronomer and I don't know if you guys are. So I included this just for y'all's benefit. Although it just occurred to me that this is flux in Jansky's, which if you're not an astronomer, that still doesn't help. I did not think that through, actually. Hope y'all are enjoying this. But anyways, next up is some lab simulations of these bright satellite trails on the Lsst camera's CCDs. So they actually picked up the camera from Lsst and were like, let's shine lasers in it. Let's do all this other stuff to test how it would actually affect Lsst's very specific electronics, because this was an Lsst case study. So they tried several different things like dithering of bright spots, shining a laser in it, projector systems, so much stuff. And eventually they found that re-imaging a 40 micrometer slit with an optical beam to form a 4-pixel wide line extending across the CCD, which is a slight tongue twister, was optimal. What they resulted in was that the satellite trails cause a lot of undesirable image artifacts. And specifically, there's crosstalk of the trail into neighboring channels of the CCD. So in the plot on the right, you can see the main trail going across the middle diagonal from top left to bottom right. And the other, I think you can actually see 6 other lines of crosstalk. So it means the actual physical cables are interfering with each other. Each CCD has 16 1-megapixel segments that are each read out by independent parallel processing channels. These are processed simultaneously at 500,000 pixels per second, which is incredible. but also this results in low-level coupling between the channels within each CCD. And unfortunately, it's not like classic capacitive coupling because it can be negative and nonlinear with respect to the main trail. And so they can attempt to mask it out and subtract it like you see in the bottom image, but that still causes issues if there's like amounts of noise or what's left over. As I said, the nonlinearity of the crosstalk is an issue, and simple masking could introduce systematic errors. What's interesting is that, don't ask me because I don't get it, but in cosmology, there's special stuff and the noise in your image actually matters because some cosmology is symmetry dependent. If you'd asked me this like a semester ago when I was in a cosmology related class, I would have understood, but at this point I don't quite remember. However, it's important. Cosmologists care about noise. And so your removal algorithm has to address these long, highly correlated ghost images at multiple places in the CCD, all while not confusing it for faint other sources or transient sources or anything else. That's difficult. So the important takeaways from the Lsst case study is that with the full constellation, avoidance is incredibly difficult and could add years onto the survey. The darkening goals for low Earth orbit satellites at 550 kilometers are 7th magnitude for the G-band or fainter. There have been attempts made to reduce reflectivity, like Darksat and VisorSat, but neither reached the recommended darkening goals. Even at 7th magnitude, these satellite trails will still exist at 100 times the sky background noise. A nonlinear crosstalk of bright trails leaves difficult to remove artifacts. So there are things not addressed in this paper that need follow-up that I will explain in the next couple slides a bit. But spectroscopy is that the Starlink reflection of the sun adds the spectrum of the star, like the sun itself, into your spectra if you're looking at the sky. Also, the satellites are much more bright while ascending and descending from their final orbit. Also, what if the other satellite companies don't actually cooperate? What if they make them super reflective? And VisorSat. Yeah, so let me get more water. I've never actually given a talk this long before. This is very exciting. So here's an example just to show you an image of VisorSat. You can see it just kind of has these little panels that stick up like a weird sort of umbrella almost. And one of their other attempts was to change the orientation role. So while they're launching the satellite and it's ascending to orbit, they have the solar panel that they can kind of roll it in a different direction so that it's not reflecting as bad, and it sort of helps. However, as we can see here, this other paper that did measurements of VisorSat declared that they think 8th magnitude is the goal to go for darkening instead of 7th, which is even better. However, you can see that the vast majority of the VisorSat measurements do not meet that goal whatsoever. That's the gray boxes. The blue boxes are the original Starlinks, and the red box is the VisorSat that actually reaches the goal of 8th magnitude or darker. So the next several slides I'm going to share are slides that I've borrowed from the Dark and Quiet Skies conference that you can actually see their talk on YouTube. It's all public. And since their slides look really pretty, I'm just going to borrow some figures from them. So let's quickly go through that. They took 567 measurements of regular Starlink satellites and found that on average, they are 4.7 magnitudes. So to be clear, this left end of the plot is, this is where we want them. You can't see them with your eyes, and so it's fainter. It's about 7th magnitude or fainter. Everything to the right of this vertical red line is showing that these satellites are too bright. Definitely too bright. Here is just further measurements, which I've already been over that, but they found that Darksat and VisorSat had similar brightnesses, but regardless, they were not good enough to be even not visible to the naked eye. They also found that both Darksat and Starlink get brighter towards the longer, redder wavelengths, which means that they are absorbing a bit more infrared, which wasn't part of the Lsst case study because they were only measuring optical, but that is interesting to note for people who care about infrared stuff. Here is a demonstration of the spectroscopy issues, is that when you take a spectrum of something in the sky, if you have Starlink and it's reflecting, it's literally adding the sun spectrum on top of whatever you're looking at. So here you can see in gray is just some random galaxy, but then in black is you've added the sun spectrum on top of it. So it is actually affecting things, which is not great. Yeah. Another important thing to note is that the orbit decay is an issue. So the planned lifetime of each of these satellites is 5 years, and then 6 months of decaying and ascending. So this means that for 6 months, each of your satellites is going to be extra bright. And then they're still bright while they're up there. And so at any given point, 10% of your constellation would be either ascending or descending. So 10% of the constellation will always be ultra bright. Here's a quick video showing from the point of view of the Lsst, just a bunch of pointings on the sky throughout the night, showing satellite trail crossings. And so you can see as you get further into the middle of the night, they'll start to die down a bit because they're all moving into the Earth's shadow. But then once it gets back towards dawn, they all act up again. I'm not going to make you watch the whole video. I'm just going to, whoops. Well, let me skip ahead to the middle. You can see in the middle of the night, there aren't nearly as many if it's like during like the part of the year where the nights are longest. But then it picks back up again as you go towards dawn. The last part of the talk is going to be a literal assessment of the costs and benefits of these satellites. So to start with, laser links and ground stations. What you may not know or realize is that, yes, you connect to the satellite to get internet, but at some point, the satellites eventually have to connect down to Earth to ground stations to physically connect to the actual internet itself. The first 955 Starlink satellites were not equipped with laser links, which means that each of these satellites requires a direct line of sight to the ground stations to connect to the internet. So if you're in Antarctica, for example, you won't get your global internet because there are no ground stations yet installed in Antarctica. So you can see here, I made a little cartoon of the satellite being within view of this one person and a ground station, but then this person over here is sad because they can't see the internet. And so here's a better illustration from a separate paper. And they did an analysis of like potential like laser links and Starlink, since it's not quite public what they can actually do or how far they can connect between each other. And so here's a demonstration of one of them connecting with another laser link and so on. And they can all connect to each other and eventually get back down to a ground station once they launch the satellites with laser links. But for now, the 1,000 or so satellites that are up in orbit right now from Starlink don't, like, they're not helping provide global internet. They're just being annoying. And so here is just this website, if you want to write it down, Satellitemap.space. It shows you where all the Starlink satellites are in real time. And it also shows you where all the ground stations are and have been installed. So right now, no one in South America can get global internet from Starlink. Now, what are the costs? I just plugged in the University of Minnesota just as an example to see what the cost is. And it is a $600 approximately down payment for the actual dish called Dishy. And then also the service is $100 per month, which which could be useful, but that's a lot. And so if you're in like a country where it's really, you're poor and you don't have money and you don't have internet, you probably can't afford the cost of Starlink to get internet. So this other analysis shows that at its current cost, which hopefully will go down, but at its current cost, Starlink isn't actually benefiting people where it's needed most because it's simply not affordable. So this is an image posted by a Reddit user in the Starlink subreddit, showing that Starlink is in fact incredibly helpful if you can afford it, because I feel that I should at the end of this talk admit the pros and cons, and the pros are important too. And it's fast. It's really fast. Like standard rural internet in the United States is pretty atrocious, like less than a megabyte per second. I wouldn't be able to give you this talk if I lived in middle of nowhere. But with Starlink, they're getting like literally faster internet than I personally have here in the Twin Cities myself. So it has its pros, and that is fast internet, which is very helpful to people who have no other way to get it because internet companies won't dig cables or fibers to middle of nowhere. But I'd like to go back once again that the cost of Starlink, the other cost, the metaphorical cost, is that satellite trails can ruin critical astronomy observations that you can't simply reschedule. If y'all recall back in 2017, there was the Oumuamua asteroid that came by the Earth, and it was the first interstellar item to visit our solar system. It was from somewhere else, and it came in. You can't simply reschedule your observation when a satellite isn't in the way. And right here in this bottom left, literally a satellite trail went over the asteroid for this telescope. So like that's what makes it, is that you can't just reschedule every observation. Some observations are time sensitive and you need to get them now. And if there are satellites in the way, there's nothing you can do. And it's not just Starlink. There are many other constellations being planned to put up there. If this feels depressing and you're asking, what can we do? Write to your local representatives, please, because we need regulations for this. Global internet is great, but if it's at the cost of astronomy, I don't know if I can accept that personally. And here's a bunch of sources of information if you guys want to look into this further. Thank you. Questions?
Thank you, Lauren. That was a great talk. So we do have some time for questions. So unmute yourself and ask questions if you do have them.
I have a couple questions. I actually spotted one of these Starlink trains before I had heard the name Starlink. I was quite shocked by it. Have you ever seen one?
Yeah, I didn't play the video here because I couldn't find where I put it on my flash drive, but I've actually seen them from the roof of Tate itself. Tate is the astronomy building, if y'all don't attend here, sorry.
So,
yeah, I've seen them quite a few times.
Okay, so here's actually my technical question, and that is, what does SpaceX think about VisorSat and about Darksat? I mean, did those satellites actually do okay, or was the fact that they were trying to help the astronomers meant that the satellites themselves were not as effective and they're not willing to or interested in continuing that process?
Allow me to answer that with a comment. Have we seen anything else further beyond VisorSat and Darksat launched? And the answer to that is no. So no, I don't think that they've put in further effort as far as I'm aware beyond that. In their minds, oh yes, we darkened it a little bit, and maybe they'll put something out in the future, but nothing that they've announced so far. They claim to like be working with astronomers, but we're not seeing those results if they are, I guess. I say this with hesitancy because maybe there aren't public news releases Like maybe there's private stuff that they haven't put out yet, but if there is, then I don't know about it yet.
Okay, I'm going to unmute Ryan. It looks like he has a question. If James, oh, there he goes. All right.
Yeah, thanks,
Ryan.
Lauren. That was a really great talk. Thanks for putting it together. I, in particular, since I haven't paid that close attention to this, hadn't appreciated the issue of the defocusing and how much worse that made the problem of the width of the tracks. And I was just wondering if you had heard anybody out there making the argument that they, okay, so I totally agree with you that this is like really devastating for ground-based astronomy in general, right? But I wonder if anybody's making the argument that they might be able to take advantage of that for like occultation studies. I know sometimes people are interested in imaging or measuring the properties of things in the outer solar system or other stars even by looking at occultations. And I just wonder if there's anybody out there that you've seen making that argument or anything else that, oh, maybe we can make some scientific hay out of this somehow.
That's a really good point. I'll actually email my friend Brian after this because he does stuff with like asteroid occultations, and I'll ask him if there's anything with that. Do you want me to email you about that?
Sure, yeah, that's interesting. Thank you.
Okay. Yeah, I will do that.
Nico, you had a question?
Yeah, hi. I may have missed this number at the beginning of the talk, and also it's changing constantly, and I feel like I'm out of date on it. Do you know how many Starlink satellites or other satellites like it are currently in the sky versus the total number of 12,000 or 48,000 you were comparing to earlier?
I think at the moment it's somewhere around like 1,300 Starlinks are up there right now, and the total number of active satellites in orbit is somewhere around 2,000 or 3,000, not including dead stuff like that are defunct and just space debris now, as far as I can recall.
So if I have seen like a Starlink trail, I will likely see at least 10 times more, if not like 40 times more of those if the full Starlink satellite constellation goes up. It sounds like just by number.
Yeah.
Thank you. That's quite a bit.
Yeah.
And if I may chime in there, keep in mind, there are also, Starlink is just one. There are a bunch of other companies out there trying to put large mega constellations up. So quite a few of them out there.
Yeah. It's like a bit of a conflict of interest because like I know people like one of my favorite YouTubers like needs Starlink because otherwise she doesn't get internet in the middle of nowhere. And it's like, man, I'm glad she has internet, but also my astronomy. It's like I understand both sides of the perspective. And so it's really hard to go into this with like a completely unbiased mind, to be honest. Yeah.
Well, I have a question if others don't, or if others are thinking of questions. So you said something to the effect that all satellite operators are not necessarily willing to share the the orbital elements, the orbital parameters of their satellites.
Yeah.
That's true, but most objects on orbit, their orbit elements are public, right? At least a crude version of it. So is the issue that you need something a lot more precise than what's publicly available, or is there something else going on where is there some other additional information that you're looking for?
Part of it is the precision, because you need to know exactly will it intersect with your object. Also, just like, for example, Space B is well, right now there's only like 8 of them, but they're planning a constellation of satellites. And like, for example, they were some tech startup in California, and they actually illegally launched their satellites from India because they couldn't get US approval. But because they were a tech startup, they were super secretive. And despite, sure, we can look and try and track these ourselves, but they were not sharing any information whatsoever. So you might not know, is this going to be a bright object we have to account for and move out of our way? Is it going to be something else? It's just there's so many uncertainties, and also the issue of if there's a supercritical astronomy event, can we ask them to move their satellite out of the way? And there's nothing obliging them to do that.
I mean, they probably won't be able to with these small ones anyway. They don't have the ability to really, they don't have much maneuvering ability anyway, so. Huh, interesting. Something I need to look into. All right. You have time for maybe 1 or 2 more questions. Anyone?
I've got a question about Cubesats. So basically, Cubesats are becoming more and more and more prevalent in orbit. Are they problematic to astronomers or not so much?
I don't know. I don't really know much, if at all, about Cubesats, to be honest. If anyone else knows, that would be appreciated. But I don't actually know much about Cubesats at all.
I don't see why they would be different, James. I mean, if they're built in such a way.
Smaller. I mean, just wondering if they're so much smaller that, 12th magnitude, who really cares or something.
How big are they, like, size-wise?
That's the rub, right? I mean, they could be small, but they're also ones that are like 27 U's, right? I mean, people are talking about bigger and bigger CubeSats. So they're like Lego blocks that people put together. So they could be as small as 10 by 10 by 10, or they could be centimeters, yep. Or they could be bigger than, you could put a bunch of those together and get something that's big. So I guess it depends on the size.
Okay.
So you just launched one, Demos, that was about the size of a loaf of bread or so.
That's a common size, but I mean, for example, Planet Labs, right? They have about 100 plus CubeSats, 3U ones in orbit. But if you look at their solar panels, they kind of, when they're fully unfurled, it's a lot bigger than a 3U. So
that sounds like it could be problematic. Yes.
right. So. All right, so I think per our schedule, is there a question?
Yeah.
Yeah, go for it.
Okay, if there's still time. So these, basically the reason that you can't account for the satellites in the images is because they're out of focus.
It's more that they're not quite. The most important reason is that they're really bright, that there's a point where they're either saturating pixels such that we can't subtract them effectively, or if they're not saturating the pixels, there's still enough of an input that there's then crosstalk in the cables that read out the pixels, which then causes repeating artifacts.
Okay.
Yeah. The out of focus just makes the trail wider, which makes it worse, but it is not the only problem.
Okay, so Demos, why don't we call that good for this session? Thank you very much, Lauren. I'm going to stop the recording and then.
Yeah, Lauren.